Goodness of fit test. Suppose we want to make an inference about a group of data instead of just one or two pieces of data. Or maybe we want to test counts of categorical data. Chi-square testing allows us to make such inferences. There are several types of chi-square tests, but in this section we'll focus on the goodness of fit test. Goodness of fit test is used to test how well one sample proportions of categories match up with the known population proportions stated in the null hypothesis. The chi-square goodness of fit test extends inference on proportions to more than two proportions by enabling us to determine if a particular population distribution has changed from a specified form. The null and alternate hypotheses do not lend themselves to symbols, so we define them with words. H0 would be that whatever our data is would be the same as the given distribution, and our alternate will be that it's different. For each problem, you will be making a table with the following values. We will need observed counts, expected counts, and then for each piece of data, we need to calculate the value of the observed minus the expected squared divided by the expected value. The sum of all those observed minus expected squares over expected is called the chi-squared test statistic. We can use a table, the calculator, or RStudio to find our p-values for chi-square with n-1 degrees of freedom. Now our value for n is not how many are in our sample, it's how many different categories we have, as you'll see in a minute. Chi-squared distributions have only positive values, and they're skewed right. The degrees of freedom increases. As the degrees of freedom increases, it becomes more normal. The total area under the chi-square curve is 1, like any other distribution. This is the graph, and we can see with degrees of freedom 2, it looks just like an exponential type curve. With 3 and 4, and as we increase more, it will get more normal in appearance. The assumptions for a chi-square goodness of fit test are: the sample must be a simple random sample from the population of interest. The population size is at least 10 times the size of the sample. And all expected counts should be at least 5. To find the probabilities for distributions on our TI-83 or 84 calculator, there's a command that's chi-squared CDF. It's under the distribution menu, the same place that we find our normal CDF and TCDF. In RStudio, the command is p-chi-sq, and we put in our test statistic and our degrees of freedom. Let's look at an example. The Mixed Up Nut Company advertises that their nuts contain by weight 40% cashews, 15 Brazil nuts, 20% almonds, and 25% peanuts. Truth in Advertising investigators took a random sample, a size of 50 pounds, of the nut mix and found the following distributions. We want to test at the 1% significance level if this claim is true. So first, we're going to write our null, which says that the distribution of nuts is the same as the population. And our alternate is that at least one proportion is different. Now in here we're not going to be concerned with which one is different. There are other tests, and you can, in other statistics classes, go a little further to find that out. Now, we have 4 different types of nuts. That's our count for N, not the 50 pounds. So our degrees of freedom is 4 minus 1, which is 3. Now, these are my sample values. These are the observed values. We need to find our expected values. So based on 50 pounds and these percentages, we're going to get our expected. Let's make a chart with our observed and our expected, and then we'll find our observed minus expected squared over expected value. So we're going to make a little table here. And I'll make our columns, and I need a row for each type of nuts. We have cashews, Brazil nuts, almonds, and peanuts. So we're going to list their names first, then we'll rewrite the observed values that we saw, then we'll find our expected values, and then we'll start calculating our statistics. So this will be observed, this will be expected, observed minus expected squared over expected. So for the cashews, we observed 15 pounds. That's this value right here. Now there was 40% cashews with 50 pounds. For the expected value, we're going to do 40% times 50 pounds, and that gives us 20 pounds is what we would expect with the cashews. For the Brazil nuts, we observed 11 pounds. We expect 15% of the 50 pounds, which gives us an expected count of 7.5. Next, we had almonds, where we observed 13 pounds, and the expected percent was 20%. So 20% of the 50 pounds, we would expect to have 10 pounds of almonds. And last, for the peanuts, we observed 11 pounds, and we were told that 25% would be the expected amount for peanuts. 25% of 50 pounds is 12.5. Now we're going to calculate the observed value, 15 minus the expected, so 15 minus 20 squared divided by 20. That gives us 1.25. 11 minus 7.5 squared divided by 7.5 is 1.63. 13 minus 10 squared divided by 10 is 0.9. 11 minus 12.5 squared divided by 12.5 is 0.18. Now we're going to add all these up. And that gives us 3.96. That is my chi-squared test statistic. We don't draw a graph on these like we did with our other ones, because again the chi-squared changes with its degrees of freedom. Now we're going to calculate our p-value. So remember, our chi-squared is 3.96, and our degrees of freedom was 4 different types here minus 1, which was 3. Now what we're going to do is I'm going to show you how to do this on the calculator. Okay, our chi-squared distribution is under the distribution menu, so second, variables. And it's down here at number 8. We use the CDF for less than, greater thans. Our lower bound will be our test statistic, 3.96. And our upper bound is just some large number. I'm going to do 10 to the 6. Our degrees of freedom here was 3. This is our p-value right here, 0.2658. This is definitely greater than our alpha, which was 0.05. So once again, we did chi-squared CDF, our test statistic, some large number, and then our degrees of freedom. Now, if we use RStudio, we would do 1 minus PCHISQ, our test statistic, and our degrees of freedom. You don't need a large number in this one. Since our p-value is greater than alpha, we will fail to reject our null hypothesis and stick with the claim that the distributions are the same as the claimed